Welcome all. As Reese said, my name's Professor Rumbold. I have been at Willamette now since 2015, and been with the Masters in Data Science program and partly a little bit of the Masters in Computer Science program now since basically their inception at this point. And so, what I wanted to sort of do this evening, when Reese asked me if I had any ideas of sort of what we could chat about, is to sort of mix together a little bit of like part of it's going to be sort of cribbed just basically straight from a lecture that I oftentimes give at the beginning of the semester. And other parts are just going to sort of flesh out a little bit more about me since I don't know any of you. And really my goal here is to try to convey to you that even if you decide to go other ways after this presentation this evening, which probably doesn't bode like reflect well on me, but that's fine. If you decide to go, other ways, do whatever you want sort of in life, why I think, for most people, there are absolutely times that you should be at least considering using a database for your data storage needs and sort of maybe testing the waters a little bit in terms of like how you could go about doing that sort of thing. So I wanted to kick things off here with a little breakdown in the sense of sort of what I wanted to talk about here. So it's mostly a little bit about like who I am, how I ended up in this particular position, because probably by most metrics, my background isn't necessarily like the standard one that you might find with someone in my position. And then talking about sort of, what are databases, like why are we maybe interested in them, or why maybe should we be interested in them? And then a little bit about sort of, okay, if you're interested now, sort of here's what the next steps might be. And those next steps might be, joining us next year and taking the full class that I teach at some point in time. But they also might be something that you can sort of do more on your own because none of these are necessarily contingent on any particular class. And I just got a few examples of sort of where I've ended up leveraging some of these skills over the last 5 to 6 years, just to give you a little bit of context for sort of how these things might appear, how they might look, and then we'll sort of wrap things up there at the end. So, as I said, I've been at Willamette now for a few years, and actually, I'm an Oregonian. I grew up in Eastern Oregon, and the sort of path that I ended up following in order to arrive where I'm at now is, well, I started off in 2003, actually up the road at Linfield. So I was a Linfield grad. I was actually a physics math major while I was there with a minor in chemistry. I was big into the natural sciences. I really liked the problem solving aspects of physics and sort of the mathematical application to sort of more like everyday, like common experiences throughout life. I played tennis throughout all the years that I was there, which was sort of formative for building leadership skills and that sort of dynamic. And I did research with a faculty advisor there, basically for all 4 years that I was there. I started the summer after my freshman year into thin film solar cells. So not actually the silicon solar cells that are sort of more common that you see in many places, but actually solar cells comprised of two sort of, or not two, several very thin layers of different metals that sort of form the same sort of binding. Benefits of them, they use a lot less material in general, and you can do things like they can be flexible and they can be rolled up and those types of things in certain cases. So throughout all this time, as part of that research, I had, we'll say, sort of started to dabble in or teach myself a little bit of some basic programming skills because we had various pieces of equipment that we wanted to be able to interface with, read values off of, those sorts of things. Heading into or finishing at Linfield, I knew what I was particularly interested in doing in life was going to be teaching at the college level. And that means I probably needed a PhD from someplace. In my sort of last few years at Linfield, I was sort of doing some soul searching in the sense of like, I really love physics, but sort of that's not really enough for a PhD. Like, what part of physics might I be actually interested in? And I ended up sort of returning back to a childhood passion of mine, which was astronomy and space. So I ended up going to New Mexico Tech, or New Mexico Institute of Mining and Technology. It's about an hour south of Albuquerque, New Mexico, for my graduate studies. It's a fairly small school, actually not particularly any larger than Willamette is. And as such, it has fairly sort of narrow focus on sort of what graduate programs it was offering. They happen to sort of have graduate programs in astrophysics or in atmospheric physics. If you're ever super keen on like hiding in a bunker on top of a mountain and calling down lightning on top of yourself, that's what those guys do, which sounds pretty sweet. But I ended up going ahead and going the sort of astrophysics route here. Um, in particular, as we're going to mention, sort of I was focused on asteroid studies. I was big into observational astronomy. I wanted something that I could like take a telescope out and look at the time. Even though, technically speaking, New Mexico Tech is sort of home to like all the control centers for the like biggest radio telescopes in the world. The VLA is like an hour away. The control center for the VLBA is actually on campus in that case. But I wanted to do something with sort of more everyday type telescopes. While I was down there, I got big into volleyball, which is what I've been sort of playing ever since. When I graduated, I had about a 6 month span or so, half year span, wherein I was employed by my former research advisor as one of the scientists at the 2.4 meter telescope on top of Magdalena Ridge. This is a little picture of that we have up here. Cool thing about the 2.4 meter telescope, that's actually the exact same as the mirror dimensions of the Hubble telescope. And in fact, the mirror that is in the Magdalena 2.4 meter scope was actually one of the mirrors that was put forth by a contractor for a bid for the telescope. And it ended up getting sort of rejected. And so it ended up sort of being repurposed into the Magdalena Ridge 2.4 meter scope. I was only there for about 6 months. My advisor knew at the time that I was really looking for teaching positions. So basically, in the summer of 2015, I got the position at Willamette University in the physics department. So when I originally arrived here, I was teaching all physics classes. My research at that time pivoted a little bit. I was looking more at asteroids burning up in Earth's atmosphere at that point in time. And then right around the sort of 2000s or so is when the sort of precursor to what is now the School of Computing and Information Sciences started to form. I'd been teaching some Python courses as part of the computer science department. And so I kind of got my foot in the door that way and then sort of segued over completely. And so these days I am teaching entirely computer science and data science courses. I don't really have any physics courses anymore outside of one sort of like course that sort of sits in between several of these that I teach as an elective each year. So this is kind of my journey to sort of where I'm at. And I want to highlight in certain parts of this journey, like the particular instances that in my head at the time, I was thinking to myself, gosh, I need a better way to organize this information. But in practice, I didn't have database skills at that point in time. So I made do with sort of honestly mucking through my own terrible methods. So, as I mentioned in graduate school, I was focused on asteroid studies, and in particular, what I was interested in are really small asteroids. So I like to describe them to people as, these small rocks that are somewhere between like basketball sized down to maybe like baseball or ping pong ball sized. So like, rocks that you could pick up and carry around. So not huge ones, not ones that are gonna like end humanity for all of us were they to hit us, but rocks that if they were to say hit a satellite or hit a space station or something along those lines are still traveling really fast and are going to absolutely destroy anything that they happen to hit generally in the process. Or at the very least, probably make it extremely unfriendly for like any humans that might have been on board at that point in time or any actual functioning machinery. So these rocks are too small to just generally be observed against the backdrop of space. And so the way that we were going about doing this is actually taking video recordings of the unlit side of the moon. So not the dark side of the moon, not the part that's on the other side that we can't see, but just, look at it on any given night, you got the illuminated portion of the moon, and then you have the part that's unilluminated. So what we were doing is essentially just taking a telescope, fixing a video camera, looking at that, and what we are looking for is these little brief flashes that would happen when a small rock smashes into the lunar surface and kicks up like basically a small explosion is sort of what's happening here. And you can see an example of this sort of above me here on the right side of the slides. The bigger image is sort of what the overall sort of video capture looked like. So you can see the sort of limb of the moon there. You can see a little timestamp sort of down across the bottom, and you can see that little brief bright spot. And then in the little sequence sort of just above me right here, you can see sort of over several frames, like a zoomed in version of that spot. So you can see generally there's a bright flash and then it sort of fades away over time as the like explosion plume sort of dissipates. What this meant for us is essentially lots and lots of nights of observations. I'd go out, I'd wheel out the telescope, I'd set it up. Generally, the telescope we were using was actually pretty small. It was just like a 14-inch Smith Cassegrain, so something I could wheel around. It was just stored in a warehouse most of the time. That meant that its tracking wasn't perfect, so I would like basically record for 15, 25 minutes or so, and then the sort of rotation of the Earth meant the things would have shifted a little bit, so I'd reposition it, do it again, and again, and again, and again, and again. And at the beginning, when we were trying to do this, it was like a proof of concept. It was like can we see these events happening? And then once we could see the events happening, it was like, oh, I wonder how many of these events we can see. And then once we started seeing more and more of these events, it was like, oh, wait, can we see enough of these events to sort of put together some meaningful statistics to try to give some description of like how many rocks of a certain size are in a certain amount of space around Earth? That was the objective. But as happens in these sorts of things, because it sort of started off gradual, it was like, okay, I don't need a great data organization scheme at the beginning because I didn't have very much data. And then over time, it like keeps on building and it keeps on building. And at some point, I realized, like 4 years into my PhD or something like this, oh, this is starting to get really intractable at this point in time. I'm starting to want to be able to do cool sorts of analysis on this. And the way that I'm storing all this or that I can handle it, it's like in different files across different folders on my system. And there was like some organization there, but not enough, we'll say. And so what I ended up pivoting to at this point in time is I'm like, I need a way to like be able to focus on this. And so I jerry-rigged myself my own sort of ghetto looking little graphical user interface that ended up looking something like this. Mind you, this isn't anything nice. This is essentially the equivalent of just slapping a bunch of pictures onto a white background and then forcibly tying some keybinds to them. So like when I pressed the key, I could cycle on to like the next impact that I had seen along the way. But it was cool and it worked for me because I was able to sort of store a bunch of different pieces of information about, what I was looking at. So you can see way over there in the far left, we have like the same sort of clip that we just saw in this case with the sort of spot where the impact happened highlighted. Sort of above me over here to the right, we can see essentially I pulled out or I mapped the latitude and longitude of where that thing hit onto the lunar surface. So I sort of had a map of the moon where things were happening. And then you can see sort of down below immediately to my, I guess to my left, a little like sort of time series of how bright the impact was over time. The brightness of the impact only makes sense if you can calibrate it in some way. So in the sort of middle, you see sort of two histograms there. Those were mapping out different calibration stars that I had to take data for on that given night. And then sort of, I might be covering it slightly, but way down here, right next to me, we have the, like, it was sort of like a little, it was meant to be like a sort of like a little lights that would toggle on to sort of flag different things. So it was just sort of like a check mark box system of like, hey, this is something that's probably like a legitimate impact. This happened during a meteor shower, so on and so forth. And this like kind of worked. It worked for like the impacts, at least, to try to keep track of all the information that was related to like a singular impact that I had seen. But what you're not seeing here that I still needed to be tracking is all of the different calibration stars that I was observing each night. And I needed information each night just about how long was I observing and how much of the moon was I observing during those clips. Even if I don't see an impact, I needed to know how much area was I looking at, how long was I observing, so that I could sort of estimate how many impacts in a given amount of time in a given amount of area was I playing around with. So, I mean, this got me through my dissertation when all is said and done. But by the end, it was really starting to fray and fall apart. Like the amounts of analysis that I wanted to be doing on it, it just wasn't set up in a way that made this necessarily easy for me to do. So when I came up to Willamette, I had to pivot a little bit. When you're in New Mexico, you're pretty much guaranteed good weather and clear skies a large portion of the time, and you need clear skies to be able to see the moon. And in fact, because I was only looking at the unlit portion of the moon, you can imagine that that limits how often I can observe because when the moon is full, there's nothing for me to observe during that time. So when I came up back to Western Oregon here, I was like, okay, I think with weather conditions, there is no chance that I'm going to get enough observing time on the moon to be able to keep up this sort of same line of observations. So I pivoted, and instead I decided, okay, what if instead of using the moon as our giant detection screen that we're looking at here, what if instead I used essentially Earth's atmosphere? And I set myself up a 360, or I guess a 180, however you want to think about it, 180 hemisphere camera to look at the entirety of the night sky. And I'm basically looking for shooting stars when asteroids were burning up in Earth's atmosphere. And the idea was by counting how many asteroids I was seeing and, how bright they were when they were burning up, I could sort of get at a similar type of analysis, a similar type of information. And so, along with some physics grads, not grad students, physics undergrad students, we went ahead and we like made this little sort of observation thing that you can sort of see right above me here. That was, meant to be set up. It sort of had this 360-degree all sky camera at the top. And it actually had an embedded Raspberry Pi system on board that was sort of doing the processing as it went, so that I was only recording actual shooting star events, not just hours and hours and hours of random clouds going across the sky. That wasn't really what I wanted to spend all my footage on. So this worked pretty well. And even knowing what I had known from graduate school, with the sense that I'm like, wow, with these types of observations, you start off small, but then you keep on gathering stuff. And eventually, if you're not keeping yourself organized from the beginning, things start to get unwieldy. Even with that in mind, and even taking better steps along the way, things still started to get a little bit unwieldy. And so around the time that I pivoted basically from physics now into computer and data science, I was rapidly sort of reaching the state of, okay, I need better ways to go about doing this. Like my best intentions are not sort of delivering on what I need them to be able to do so that I can do the analysis that I want to be able to sort of do for this thing. And so the result is that when I moved over to computer science and data science, one of the things that they really needed at the time was someone to teach classes on databases and database management. And I sort of thought to myself, well, this is something that I'm very interested in because I now have a repeated history of seeing the downsides of when this isn't done well. And it's sort of like, this is something that the department needs. This is like a niche that I could fill. And so I've essentially stepped like full tilt into that general role. And I've been the predominant sort of database instructor for like the last 5 years at this particular point. That means we've had several iterations of an undergrad version of our database class, which we call Data 351 or data management with SQL. And then I've also taught both multiple semesters, but multiple class sections per semester of our graduate database course. Both of these courses are courses that the department as a whole, whether it's computer science or data science, feel are quite critical to anyone going into these fields in this day of age. regardless of whether you're in computer science or data science at this point, if you're an undergrad at Willamette, you have to take Data 351 at some point in time. And if you are a graduate student, whether you're an MSDS or an MSCS, you are either required to or strongly recommended to do so as well. So this is sort of what I have predominantly been doing. I still also teach some of the intro programming courses because I love sort of working with folks learning how to problem solve at that level. And then I have also been teaching an elective that sort of sits at the intersection of all my interests, which is kind of at the intersection of science, data science, and computer science. That I call that Data in the Cosmos. That's taught at the undergrad level. So I'm teaching that again this coming spring. So all that said now, I'm like, okay, that's my motivation story for why good data management and good data storage techniques can smooth a lot of problems that you might have along the way and can be very sort of future looking to say, I might not have issues with organizing the data that I have right now, but in another 2, 3, 4 years, if I keep building it at the current rate, and if we're being honest, everything's gathering data at a faster and faster rate each year, like how can I make sure that I'm organized and that I can use all this information that I'm gathering? So, I want to talk a little bit then about like what do I mean when I'm talking about a database? Many people have heard the term before. Some people might have visions of what a database is in their head. And all those things, can be totally applicable, but there's probably a little bit more than many people are necessarily aware of. Starting with the fact that there's a lot of different types of databases. So I love this little picture that I grabbed from a text that I taught out of several years ago called Understanding Data Intensive Applications or Designing Data Intensive Applications. And it sort of had these little maps at the beginning of each chapter that was sort of conceptually lay out some of the topics from that particular chapter. And I really love this one that was from chapter 1, essentially, which is this is sort of the lay of the land in the land of databases here. And the main things that I really want to sort of like indicate to you are that there's a lot of different types of databases that we can see. So up here, actually, let's switch text here or color. So you sort of have up in this region, initially, these are what we generally refer to as the relational databases. These are databases that oftentimes look very similar to tables and sort of store their information in a sort of tabular fashion. Up yonder over here, we have what are oftentimes called the document type databases. These are databases that tend to store information together that sort of belongs together, so to speak. So if I had a whole bunch of information about, say, one particular employee, I might store all that information in a general document that houses all the information about that employee. Document style databases make it really useful if I want to get information about a certain thing, maybe a little bit less useful if what I want to do is compare across 1,800 different employees or something along those lines. The other big region that sort of exists here is hanging out in the middle. It's this sort of mountain region that we have. These are what we call graph databases. So these are oftentimes databases that are really built fundamentally around understanding networks of things, or many what we'd call many-to-many relationships. So if you think about, say, any social network that we might have these days, whether that's Facebook, Twitter, whatever the case might be, Instagram, in those situations, generally you are following information from many people, and many people might be following information from you. It turns out it turns out graph-based databases are particularly well suited for representing and asking questions about that type of material. So those are like the three sort of big environments that we have going on here, but it's certainly not all of them, because you'll see sort of we have out here in this area what are called sort of column-based databases. These are databases that are more built for doing large scale aggregation. And it turns out that if you organize things by columns, that makes that a little bit easier. You have other types down here that are built more around keys and values. Those are similar to document databases, but they tend to be a sort of a little bit more strict with only doing keys and values for everything. So there's a lot of different types of databases that are out there, and each one generally has its sort of strengths and weaknesses in terms of what it's going to do well, maybe what it's not going to do as well. Of the sort of big three, though, probably the biggest elephant still in the room is the relational type databases. They've been around since like the 70s, and honestly, there's still a huge amount of information across corporations that are stored in these types of databases. And so in most of our database courses, this is what we foundationally sort of study and look at. It's like, okay, let's make sure we understand how relational databases work. And if we have some time later, we can sort of experiment or look around at some of these others. There's a chance actually that this next summer, or maybe the summer after that, I might be getting a chance to sort of offer a sort of second semester version of our data engineering courses, which would probably look into some of these other types of databases a little bit more closely. But starting with the relational, wow, let's try that again. Starting with the relational databases here, like we probably got to understand what we're even talking about initially. Like, what do we mean by a relational database? I told you that they're mostly built around these sort of, table-like structures. But what do they do special beyond that? And so I always find when I'm introducing these to my classes early on that I feel like it helps to have a little bit of a concrete example here that we can look at, both in the cases of where does this work well, and then where does it maybe start falling apart. So my little example here is to say, okay, let's say that I'm very forgetful, and I wanted to store, what all my friends' birthdays are so that I can make sure that I wish them happy birthday when that day rolls around. If I just had like a list of friends' names, and each friend has one corresponding birthday associated with when they were born, as far as I'm aware, that's something I could easily represent in a table, right? I could just do something maybe along these lines. I could say, look, I'm going to keep track of their first names, their last names, and then when their birthday happens to be, right? That's easy. It's straightforward. We've probably all represented information in this way at some form or some time. Spreadsheets are incredibly ubiquitous these days. This is essentially what that is. We're just dumping this information into a gridded cellular sort of table structure. But what if I wanted to store a little bit more information? What if I wanted to know not only when my friends' birthdays were, but I'm going to go take a bunch of classes this semester, and I want to know what classes my friends are taking so that I know essentially when they're available. I could ask other questions like, are these friends going to be in the same class together? If I want to hang out at this given time, would these friends be available? Maybe I want to combine those things, and I want to be able to ask, hey, does such and such a friend have any classes on their birthday? Or when can we celebrate? Something along those lines. Now, if I want to add this information to the existing table that I had, I got to start getting a little bit clever here. Or at least thinking a little bit outside the box in the sense of like, how can I store all this information? Because in a true table, I'm allowed essentially one piece of information in each given cell. That's kind of important because that makes it very clear if I want to go ask what is in a given cell, I get one piece of information. So if I want to take the birthday information that I had previously, and then I wanted to add in information about what classes each friend is taking and when those classes might be meeting, I can do that in a single table, but it's going to require some sort of duplication along the way. So this is what I might end up with in a given situation. And there's a few things that I sort of want to particularly highlight for you here. One, this is storing all the information that I want. It's storing my friends, it's storing what their birthday is, and it is storing a record of all the classes they are taking and when those classes happen to be meeting. Okay, so it works. However, it looking at it, you might sort of identify that this feels less than ideal. Probably the most obvious thing that we might look at initially here is that there's all this duplicated information. So, like, I have my friends' names showing up multiple times up here with their birthday. I have these other friends, Tessa is showing up 3 different times along with their birthday, and so on and so forth. Bobby's showing up twice down here. So at the very least, I'm duplicating information about my friends' birthdays so that for any given row, I could pluck out all the things that I wanted. And remember, when we're trying to abide by a strict table here, I don't get the option to like merge across columns or merge across rows in these sorts of ways. I need one piece of information for each cell, and I need an equal number of columns in each row, or vice versa. I need an equal number of rows in each column. You might also notice if we look at this, there's more duplicated information than just that. Because, for instance, I have stored the information that CS151 is starting at 150 on Monday, Wednesday, Friday in 2 different lines here. In some ways, that might even be more nefarious than the other ones, because these ones aren't next to one another, so it's not clear to me, at a glance maybe, that I have duplicated more information along the way. And similarly with some of these other classes. Now, this is problematic for a whole host of reasons, but many of them revolve around this idea that duplicating data in our storage structures is bad. And it's not bad for one reason, it's actually bad for a whole host of reasons, okay? Maybe the initial one that many people think of is that it is bad because we're wasting storage, essentially. Like, I already know that Frank Stein's birthday is on April 2nd. I don't need to store that again and again and again and again and again. So on the one hand, it's just wasteful. But there's also other problems with it along the way. Coming along the road with, what if I need to change some of this information at some point in time? Now, birthdays are probably an example of something that's generally not going to change. Once you're born, your birthday is pretty fixed. I'm pretty confident that I'm not going to need to update Frank's birthday at some point in time. But what about these classes? Say CS151 was originally supposed to be offered Monday, Wednesday, Friday at 1 p.m., but then due to some scheduling conflicts or something along the line there, it got moved. It got moved to, say, starting at 2:10 p.m. instead. If I have duplicated that information throughout my table, once any of that information changes, I need to be very careful to go through my table row by row and make sure that I update each and every row that pertains to that particular piece of information. Is this doable? Yes. Does it increase the chances that something is going to be missed and that then I would have inconsistent data in my table? Yes, it does increase those chances. For instance, if I missed one of them, and now I have 2 spots on my table, one where I say CS151 is happening at 1 p.m., and one where I say CS151 is happening at 2:10 p.m., I don't know which one to trust anymore. I don't know what the ground truth is. That information has become largely useless to me. And so we want to build tables, we want to store information in a way that sort of deduplicates it as much as possible, that resists storing duplicate information, but I still want to be able to know which class each friend is taking. And so the approach that relational databases take is that they say, wait, okay, so what we're really trying to store here is kind of 2 different things. I want to keep track of my friends and maybe information about that specific friend. But then in this case, I also want to be storing information about the classes and information about that specific class. So what we really want here is we want 2 tables, right? One that's just going, I can't tell which direction I'm pointing. It's inverted. Darn it. One which is going to take care of all the friends, and then the other which is going to take care of all the classes. Now, doing this ensures that I don't have duplicate information anymore. Each friend shows up once along with their birthday. Each class shows up once along with their birthday. And this also means that if something needs to change somewhere along the line, there is one and only one place that I need to change that piece of information. If CS151 changes from being offered at 1 p.m. to being offered at 2:10, I change that one row. In fact, I change that one column and that one row, and I'm done. I don't need to worry about corrupting my database by missing some updates that I needed to make along the way. Now, the core of this, though, was that I needed to know which friends are actually attending which classes. And so this is where we get into the actual relational part of this. The logic here is that we want to, within these two tables, also keep track of relationships between the rows within those tables. So for instance, if I jump back here really fast, I knew that Frank was taking CS 151 and Math 256. So you can imagine that what I'm trying to maintain here is that there's this sort of relationship between Frank's row in my friends table and these two particular rows in the classes table. And of course, I could do that for all of these along the way. I think Tessa was also taking CS 151, but then was like taking IDS and history or something along these lines. So I want to be able to maintain these relationships between data that is in one table to data that is in another table. And there's a variety of ways that we can do this with relational databases. For certain types of relations, we can just basically say that there's a relationship between these. For this type of situation where I have multiple friends that are taking sort of multiple classes, generally the way we'd end up going about building this is with a third table sort of along the way. A table that represents all of the relationships, all of the linkages between my friends. And then in our relational database, we would stipulate that certain values that show up in one table will also always show up in another table. For instance, in my enrollment table, which I have down here, for some reason, my little lines didn't draw, but that's fine. I can draw them myself. The idea here is that each friend is going to show up as one of these friend IDs. Okay, so if I have a friend ID of 5, what I'm going to guarantee in my relational database is that if a 5 shows up in my friend ID column in my enrollment table, a 5 is also going to show up somewhere in my friends table. In fact, we're guaranteed it's going to show up one time. So oftentimes we draw these relationships with this little sort of arrow or like little crow's foot structure going on here. And what we're saying is that the friend ID will show up once in this table, but it might show up many times in this particular table. And similarly, we might do the same thing with the classes. We'd say, okay, I have a class ID over here. That class ID might show up multiple times in my enrollment table because many people are going to be taking a single class. Just like I might have many friends also taking a particular class along the way. And generally we need some way to be able to connect these. And so you need some sort of unique key to be able to unambiguously say, hey, this row in this table corresponds to this row in this other table. So oftentimes we'll come up with unique ways that we could identify each row within the table, and then we build the relationships between them in this fashion. The terrific thing about this is that it helps us with our data deduplication efforts. That is a mouthful. But also it builds in explicit dependencies between the information that we have so that we can still store things in these different tables, but we can maintain the relationships between that information that we're going to want to have for later analysis. So we're going to see some examples of this here in just a moment, but I want to take a quick chunk here to say, okay, we've all used basic sort of table storage type environments in the past. We've used spreadsheets, or almost assuredly we've used spreadsheets in some way. You've probably taught, Excel at some point in time. Maybe you still use Excel, maybe you use Google Sheets, maybe you use something else. How does this differ from just using spreadsheets? Because honestly, at the end of the day, I'm like, I could make tables with these sorts of information in them in a spreadsheet. So what's the difference, right? So I want to spell out sort of a few of the differences. Some of these are pros, some of these might be cons, and then I'm going to sort of highlight sort of what the pros are in my vision. First off, big difference between databases and spreadsheets. Databases are much more rigid in what information we can put into them. Essentially, when we make a table in a database, we state up front, these are the columns that this table is going to have, and this is the type of information that is going to be in each of those columns. And no other types of information is allowed in that particular column. Okay, that's in stark contrast to like if I just open up a spreadsheet, I pretty much have carte blanche as to I can add some more columns over here whenever I need. Those columns might all have the same stuff in them, but they might not, you know. I can do whatever I want. It's very flexible, but that can also stab us in the back when it comes to database management. And along the way, each row is just representing a single observation. And they go in, one at a time. So you can't have gaps or something along those lines in your tables. Other differences. Generally, if I want to do some sort of calculations in a spreadsheet, what I tend to end up doing is to say, all right, let me like type out this sort of equation or something in one of these cells, drag that cell above, down the column or something like that, populate it for a whole bunch of rows, something along those lines. Now, what I essentially have is a new column in my spreadsheet that has all these calculations. In databases, this doesn't tend to be the way that we do this. We tend to sort of make the calculations we need on the fly when we want to ask questions of the database. We don't sort of populate another column, so to speak, every single time we need to sort of like add a bunch of values across columns. We could do that if I have a particularly expensive calculation that I want to just do once and never do again. But in general, we do the sort of calculations as we need them. And this helps keep a clear distinction between this is my original data and this is the data that has been derived from that data. Oftentimes in spreadsheets, those boundaries can start to merge, and it can make it a little bit confusing at times to know, am I dealing with like the original ground truth information, or am I dealing with something that has been built off of that along the way? Of course, in databases as well, it's just tabular structures to store information. There's no coloring, there's no formatting, there's no visualizations or anything like that. It is just for storing the information. If you want to analyze that information, if you want to make pretty graphics or anything along those lines, you're generally going to use an alternative tool to do that sort of thing. So these are probably what I consider like the biggest differences between these. But these also help sort of describe what I think then are some of the benefits. And I'll mention the cons as well. So benefits, biggest, and I think hands down the elephant in the room as far as like what is being brought to the table here is data integrity. Okay. Because we have columns that enforce types, that means that if someone accidentally or purposefully tries to enter in a piece of information that just doesn't belong in a particular column, it's never going to get inserted into that column. The database is going to reject it at the time that someone tries to enter it in. This is generally a good thing because it ensures that down the line, when I want to go ahead and do a bunch of analysis on the information that's in that column, I don't have to then do a ton of data cleaning to sort of throw out all the bad results and the things that I'm like, how did someone enter in like the, capital of Mexico into this column that was supposed to have a number between 1 and 10 or something along those lines? It just prevents that from happening. And it enforces these relationships between our tables, for instance, so that if I say, hey, a value that shows up in this table is also going to show up in this other table, if someone tries to insert a value into just one of those tables, the database will say no, and it'll stop them at that point, and we don't get that sort of corrupted or corruption of data into our system. So this is probably up and away like the biggest benefit that we can sort of have in this situation. If you're dealing with huge amounts of records, like in the millions, you're going to get so much better performance from a database than you are from a spreadsheet-based system. I would imagine many people have felt the pain of opening a spreadsheet that has like thousands and thousands and thousands of rows in it. We're going to look at a database here in a little bit, as long as I keep moving along here, that has upwards like millions of rows within it. And you're going to have databases that have billions of rows within them. Spreadsheets weren't meant for that sort of storage, and they tend to bog down and perform horribly should you ask them to try to handle that sort of thing. Also, this is maybe a little bit less of an issue in some ways because we have things like Google Sheets these days that you can also easily share with other people. Excel can also do sort of multi-user access in this way as well. But in particular with databases, you can really lock down exactly what information in the database is someone allowed to see. That's something that I have repeatedly not been able to replicate to the same level in any sort of spreadsheet program. Of course, we've talked about how this sort of helps us remove duplicate information and the things that can arise there. Pretty much all databases have excellent support for pretty much any scripting or coding language that is at all popular at the moment. And so while you might need these third-party tools to be able to sort of analyze and work with it, they're built to sort of mesh very nicely with these types of systems. And then last but not least, and I think this is absolutely a pro in this case, it separates the information that you're storing from where you are analyzing that information. And depending on your workflow, this may be more important, it may be less important. But what I have generally found is as you accrue more information, maintaining this separation becomes more and more important. Because 3 months from now, when I want to access a particular piece of information, I don't want to have to wade through the analysis that I did today with that information to find the underlying information. I just want to be able to jump to where's the ground truth information? Let me work with that. And so the way that we tend to implement these sorts of things, the way that we work with these sorts of relational databases is with a scripting language, so to speak, called SQL. Or historically, you'll oftentimes still hear it referred to as SQL. Okay, but it technically just has the abbreviations SQL at this point in time. The S, the Q, and the L don't actually technically stand for anything in this day of age. You'll oftentimes hear folks refer to it as like a structured query language. That kind of is descriptive of it, or at least tells you some pieces of information about it. But the S and the Q and the L don't really stand for anything. It is a declarative language, which generally means that it's a language wherein we tell the computer what we want to have happen, and then sort of behind the curtain, the computer figures out how to make that happen and then does it. This tends to mean that it's pretty straightforward for folks to learn. It sort of has a sort of English language flow to many aspects of it that sort of keeps it looking nice. You can use it to manage the database. That is to say, make new tables, add things to tables, change things in tables. But you also tend to use it to access information from the database and grab information. So I have below just like a little snippet or an example of like what that might look like for if you're trying to extract some information from a given table. And the main things I want to sort of highlight to you here, the things in purple are the sort of SQL keywords. The things in sort of teal are just where you would fill in the information that you are particularly interested in. So that I could say, look, I want to grab all these columns worth of information from this particular table. I only want the rows where this particular thing is true, so I can filter down some of the rows to just get the rows that I want. Oh, and by the way, once you've gathered all that information for me, which would also be in a table, please order that table by this particular column, because maybe that's what I'm interested in. I want to know what the biggest values were that I had in this particular situation. That's the sort of flow behind how this tends to work. And there's, of course, more complexity that can come up along the way. But in my opinion, especially compared to other languages, SQL is extremely approachable. And so it's not too much of a leap to at least get the sort of baseline skill set to know how could I interface with these types of systems. Now, if you're thinking to yourself at this point, like, hey, I might have some use cases for this along the way. I just want to give you like a broad brushstrokes of like how you might go about getting into this. Because I think there's sort of a few ways that we could do so. The first thing that you do need to realize, and this is a little bit of a thing that puts people off of relational databases, I think sometimes, is that like many things, there are many formats that sort of relational databases come in. Like you saw all those little cities on the early map, those are all variants of a relational database. Some of them are closed source, some of them are proprietary, and you got to pay for them, but many of them are free and open source. All of them tend to revolve around sort of a core standard SQL syntax, but then they sort of maybe expand on it in some ways from that form. Okay, so the core SQL that you might learn for one is generally going to be applicable to a bunch of other cases. I think if you're interested in getting sort of started in this, there's sort of two main ways that you can sort of look at that. The first of which is a format called SQLite or SQLite. SQLite is sort of this crazy, tiny little program that is kind of crazy when you think about like what it can do. Essentially, the way it works is it stores a database in a single file. This can be extremely useful to you if you're used to like being able to use your basic sort of file operations to work with the data that you have. So that I could store a database in a single file. I could stick that on a thumb drive or something, give it to someone else, email it to someone. They could access it in the same way. That's kind of useful. But inside that single file is all these relational database things that we've talked about. SQL is actually, or SQLite's actually so tiny that it doesn't even need an install. It's just an executable that you can sort of download like in a zip file, and you can just run it on your system. And in fact, these days, it's even getting more and more popular that people are just embedding SQLite databases on a like individual level if they're trying to write a, say, cloud computing app that's going to sort of serve up a lot of information to various individuals. Rather than talking back to a central database, they'll just spin up little SQLite databases on each person's individual system, and it makes the data retrieval really fast. Pretty much any programming language can interface nicely with SQLite databases, and it's just a great starting point because it's very low stakes. If you want something a little bit bigger, many other types of databases operate on a sort of central server model, okay? And so in this case, the database itself lives on a server that sort of operates as a hub. So various people can connect to that server, they could ask information about it, they could maybe make changes to it, but then they could disconnect it from it at the end of the day. So really it's built around lots of people potentially accessing the server or the database at the same time. Big examples of this are PostgreSQL, MySQL, SQL Server, Oracle SQL. These are all sort of things that operate on this fashion. We've generally been teaching PostgreSQL in our classes, and I've been very happy with it so far. Doing a server install is a little bit more complicated, but there are easy ways to sort of go about doing it. And I sort of have a few of them here. And I can also link these slides to Reese at the end of this so that they can get shared with you all if you're interested in them. The other thing that sometimes comes up when we have a server model is we need to be able to connect to that server. And this is, we need a client to connect to it. And so wherever that server is, it might be on a system we have, it might be on one of like these big cloud platforms we can do, it might be on like a smaller little provider like Railway, but wherever that server is, we need a client to be able to connect to it. And if you thought there was a lot of different variants in the sort of different possible relational databases that are out there, there's even more variance in the number of like clients that people use to connect to those different sorts of databases. Many clients are sort of multi-purpose, like a single client could connect to this type of database or this type or this type or this type. So you don't tend to need to learn a whole bunch of them. My favorite client at the moment that I've been using extensively is called Beekeeper Studio, in particular, the open source community edition. There's another popular open source one called dbeaver that's very common. What these generally allow you to do is they allow you to connect to a database and then see what tables are available, run SQL commands against that database, maybe edit the tables directly, these types of things. So I think what I want to do here, since we're largely tight on time, or at least in like these last sort of 5 minutes, if you'll give me those, is to showcase to you at least one sort of example of what this might look like, and then sort of wrap things up at that point. So there's a few areas that I have sort of incorporated databases into my everyday sort of workflow at this point in time. First and foremost, I am an educator. And so most of my sort of applications of databases have pertained to trying to help give me a better handle over the information that lets me do a better job teaching along the way. So one of the first of these that came up years and years ago was I wanted a system wherein in class I could have in-class polling questions. Students can answer those questions. I wasn't using any third-party service. I was keeping it all local. Privacy was, strong in that respect, and I could interface with it in any way that I wanted. What I ended up doing for that is I utilized actually a small SQLite database. And this is actually largely, I think this was like my first project that was really using a database in this case. And so if I jump over to, not here, here, yes, okay. This is what I wanted to sort of showcase to you. In this case, this is an example of what the Beekeeper Community Edition client looks like. I have connected to my polling SQLite database. And so you can see over here on the right side of the screen, I have my various tables that I have made for this particular database. This one's not hugely complicated. It's just storing information about what questions that I might ask in class and what the responses to those questions are. And so within Beekeeper itself, you can see up at the top, I of course have this space where I could type out queries if I wanted to run them, but I can also look at what are the columns that make up each of these tables. And I could look at the tables themselves. I could say, look at and say, okay, what's going on with the questions table over here? And you'll see this is a record of every question that I have asked in class since I guess 2019, and the associated answer that was sort of the correct answer to that particular polling question. And then I have another one for student submissions. So that if I look at this, these are all the responses that would have been made to a particular question and what that student answered along the way. And where's the relationship here? Well, in the submissions table, there's this question ID, and that question ID corresponds to this column in this other table. That's how I connect the things together. And this is just a small example of how this can be done. I've expanded this to sort of storing my entire grade system in across about 15 different tables now, to accomplish similar types of things. It's a lot more complicated. It stores a lot more information, but at the end of the day, it's a set of tables that are linked together with these different relationships. And so what I want to leave you with is a little bit of a conclusion then about sort of why I think it's worth looking into actually using a database should you be needing to store information. Okay, so most of this we've already talked about in this case, but here's a sort of pros and cons list. I think of where both of these have their places, because don't get me wrong, I do think spreadsheets still have their place. I'm not like a database or bust type person in this case. But if what you are looking to do is store gradually increasing amounts of information over a large amount of time, absolutely, I think you should be looking into a database for that sort of thing. It could be a really simple one. It could be a little SQLite database with a few tables in it that's just stored as a file that you can, pass around however you need. Or it could be something big and complicated. But for those types of situations, over time, it will make your life so much easier, both in how you access the information and in the knowledge that you are maintaining the data integrity of that information. If, on the other hand, what you need is a very multi-purpose flexible tool wherein you can make some quick changes to some data, maybe throw up a quick graph, something along these lines, spreadsheets are amazing at that sort of thing. And so, don't hesitate to use spreadsheets of that type when those sorts of use cases are pertinent. Like that's the tool for the job in those types of cases. But once your data reaches a sort of certain threshold of complexity and size, then's the time that I sort of highly recommend you sort of swap things over. So, with that, that's pretty much what I had sort of planned to chat with you all about tonight. Thank you all for sort of showing up on a Thursday night and sort of putting up with me. Um, Mainly, I just want to convey to you that like adopting more databases in my sort of everyday workflow has, I feel like, vastly and powerfully impacted the way I operate on like a very positive sense over like the last sort of 5 or 6 years that I've really gotten serious about going ahead and doing this. And with that, like I'm gonna sort of wrap things up. Reese, if you have anything else that you'd like to talk about, or if anyone has sort of any questions or anything like that that they'd like to bounce off of me, I'm sort of more than happy to sort of stay a few minutes here and answer some questions. But thank you all.
Yeah, thank you everybody for showing up. I hope you learned something or at least got a glimpse into kind of what some of our classes might be like or Professor Rumbold's teaching style, anything like that. But thank you all for coming. If you have any questions for either of us, feel free to stick around and ask them. Um, but yeah, I would love to meet with any of you one-on-one if you are seriously considering a master's degree or a program, and I can help with anything in terms of questions about the programs, application kind of stuff, anything like that. But it'd be great to see all of you if I haven't met you yet. So thanks.
I do have a quick question.
Yeah.
So what was for this evening's lecture, how much of that is covered in like, for the master's program, like the database? Like what exactly is the overlap between what went over and
Yeah,
yeah.
absolutely. So, the our fun what we call our fundamentals of data engineering course, which is largely what this was sort of cribbed from. I see it as sort of having two main roles that it tends to fill. One of those roles is making sure that anyone that goes through our program knows the ins and outs of how to write SQL queries and interface with these databases. So, like, sort of half the class is SQL based to make sure that people can do those sorts of things. The other half of it, I sort of see as the other part of what goes into sort of these data management type pipelines. It's looking more at, okay, how can we think about how to ingest information into our databases and maybe do several like transforming or cleaning steps automatically, and then ideally at the end be able to serve it up to someone else to actually be able to do something constructive with.
Okay, that makes
So
sense.
those are kind of the two pieces that we tend to sort of focus on over the semester.
Okay. Yeah, and when you showed that map of the different like databases, like talking about them, how much of that would you necessarily cover in the like first class?
So in this particular class, for the most part, we just focus around relational databases.
Yes.
The others are we just basically run out of time. And so should
Yeah.
I get the opportunity to like teach a follow-up to it, we will
Yes.
absolutely talk about some of them in that case. I've also had some people, we have like a final sort of project that goes on in this.
Yes.
Sometimes I have some folks try to sort of incorporate some of those if they're interested in them in that sense. But
Of
in
course.
the class itself, we don't really get a chance to go into them, unfortunately.
Okay, thank you. That answers my questions.
Perfect.
Thanks.
Yeah. Thanks.